welcome to the class. So in today's class, we'll be discussing states of matter of chemistry. It has common concepts in thermal physics as well, so it would help you out in physics too.
Assalamu alaikum everyone, welcome to the class. So in today's class we'll be studying states of matter from chemistry. This is the chapter number 1 as per the Cambridge's syllabus, IGCSE as well as O levels. We'll be discussing concepts from both O levels as well as IGCSE for states of matter. For those who take physics, this these concepts that we'll be studying today are common in physics as well. So this is part of the kinetic model of matter in thermal physics for your syllabus. So those taking physics, they can also watch this lecture so that it will help them out in physics as well. Before we get started, I'll like to give some details about myself. My name is Harun Tariq, and I had really good, really impressive grades in my back in the day when I was giving O levels, IGCSEs, and A levels. And Alhamdulillah, I have 7 world records in O levels, A levels, and IGCSE with numerous A grades and A star grades. Um, and Alhamdulillah, I've been teaching for around 10ish years now. O levels, IGCSE, as well as A levels. Over the course of this academic year, we'll be discussing all the syllabus, including this chapter number 1, which is states of matter. So let us get started then. Let us discuss the 3 states of matter. We have 3 states of matter: solids, liquids, and gases. We'll first discuss solids. Now, their arrangement. What do we see on our screen? We see a very regular arrangement, don't we? There are close to no empty spaces in between. We see a very regular pattern. So I'll just write the characteristics now. We see a regular pattern. The second thing that we see over here is the particles are quite close to each other. That must be because there are a lot of attractive forces between these particles. Those strong attractive forces between particles is what is keeping them in close contact, right? So we can say strong forces of attraction between particles. Now, the arrangement over here is such that the solids, these particles cannot move around. So for example, if I have this particle A, now this particle A can't move around and let's say reach over here, or move and reach this position over here. No, the particles in a solid, they cannot move around. They actually just vibrate about their fixed positions. So what this particle A would do is, it would just vibrate. This would be true for all the particles over here in a solid. So it can only vibrate, let's say, in this direction or in this direction, in this direction, and it comes back to its original position. It only just vibrates slightly, and there would be only slight vibration. There would be no moving around inside the space. So we can say particles, particles in a solid, of course, move, or movement would not be the correct word. The proper terminology should be particles only vibrate. They don't move around, they only vibrate. Particles vibrate about their fixed positions. Right? Now, the volume in a solid. The volume over here is fixed. You see, there are very limited empty spaces in between. So it has a fixed volume. The particles are compact. It would not be possible for us to bring these particles closer together. So fixed volume. What fixed volume would mean? Because the volume is fixed, they can't be compressed. They can't be brought any closer. We can't bring them closer together, right? So the volume is fixed. So they can't be compressed. Can't be compressed. Okay. Now the shape over here. For example, if we take water, we pour that water. Let's say it is in a glass. If we pour it in a jug, the water would take the shape of the jug. Initially, when it was in a glass, it had the shape of the glass. So water or liquids basically takes the shape of the container. But for solids, if we have a, let's say, metal cube, if you put it in a jug, it will be in the same shape as a metal cube, whether you put it in a glass or any other container. So solids, they have a fixed shape. They have a fixed shape. They do not take the shape of the container. Fixed shape. So these are the general properties that are examinable for solids. So you need to memorize all these properties. Now for liquids, we'll discuss similar properties now for liquids. What we see over here is uh, we don't see a regular pattern anymore. So we'll say irregular pattern now. Irregular, or you can say random pattern. Now for liquids, these particles that you see, let's say this is particle A, is this can actually move around and let's say reach this position over here, or move around and let's say take the position of this other particle over here, or this particle over here. So in a liquid, the particles don't really vibrate about their fixed positions as was the case for solids. They actually move around in the confined space of a solid. They can move around, right? In this confined space. This is in a container, so in this confined space, it can move around here and there. All these particles that you see. So their movement would be the particles move around in a confined space. That is, they slide over each other. The particles slide over each other. Now, the forces of attraction over here would not be as strong as was the case for solids. The particles are still quite close to each other, not as close as solids, but not as far apart as gases either. So, forces of attraction are still quite strong. Of course, not as strong as solids. Strong forces of attraction. If we say these are strong forces of attraction, then in case of solids, it would be very strong forces of attraction. They are stronger than liquids, right? The volume over here for liquids, although we see some empty spaces in between, but for our syllabus, liquids can actually in reality be slightly compressed, but that is not what we'll state in our exam. In our syllabus, we'll say they have a fixed volume. They have a fixed volume. Because they have a fixed volume, they can't be compressed, just like a solid. Can't be compressed. Okay. So as we have discussed the movement of particles, and they take the shape of the container. They do not have a fixed shape like a solid. They take the shape of the container. Take containers shape. Okay, now as far as kinetic energy of particles is concerned, what like in a solid, the particles could only vibrate about their fixed positions. But over here, the particles, these particles that you see, or molecules or atoms that you see over here, can actually move around in a confined space. They can slide over one another. So kinetic energy is energy related to movement of particles. The greater the movement, the greater the kinetic energy. So for liquids, the kinetic energy is actually stronger than the kinetic energy of particles in a solid. So we'll say higher kinetic energy than solids. Of course, these would be weaker than uh, gases, but higher than solids. So we'll just go back and write this point over here as well. Weakest weakest kinetic energy for particles. Okay, now let's move on to gases. This is more or less the arrangement of particles in a gas. So what we see over here is irregular arrangement, just like for liquid. So we will say irregular slash random arrangement. We see a lot of empty spaces in between. So the movement over here will be uh, fast movement in all directions. And because the movement is very fast, so highest kinetic energy over here, highest kinetic energy. Next thing that we see over here is there is a lot of empty spaces in between. So it doesn't really have any fixed volume. We can bring them closer together, right? So if we, for example, push this container from this side, let's say it was a piston. If we move this inwards, this particle just would just adjust its position within the confined space, right? So we can actually compress this particle over here. So we can write over here that uh, volume not fixed. Volume is not fixed. Can be compressed. The other two were can't be compressed. This is can be compressed. Okay, now this can be compressed. Now, what about its shape? For liquids, it took the shape of the container. For solids, they had fixed shape. This does not have a fixed shape. No fixed shape. Just like liquids, because it is a fluid. Fluid is anything that flows. Liquids and gases both are fluids, so they can flow basically. So no fixed shape. Take takes the shape of the container. So these are the general properties of solids, liquids, and gas. Whatever was written on these slides, all these points are examinable. You need to memorize them. Okay, now this is a summary. Basically, you see, if you are asked to draw, this is how you draw your shapes for solids, liquids, and gases. Now, everything that we previously discussed. So arrangement of particles, as I told you guys, for solids you can see regular pattern, liquids random arrangement, and for gases there is random arrangement as well. Uh, as far as movement of particles is concerned, you can see vibrate about a fixed position for solids, move around each other or can slide over one another, and for gases move quickly in all directions. Like whatever space is available, they can move quickly in all directions. And we have discussed the energies as well, solids having the least energy, gases having the highest energy, and the diagrams, the 2D diagrams, as you can see over here, these are examinable as well. Now as far as density is concerned, solids, they have the highest density. Density, you must have studied this in physics, but if you haven't, density is mass over volume. So solids, they, like for a limited volume, they have the highest mass because the particles are close to each other, so there are close to no empty spaces in between. That is why their density is highest. So the closer the particles are to each other in a confined space, the greater the density. So solids, they'll have the highest density, and as far as liquids are concerned, somewhere in between. For gases, they have the lowest density, right? Okay, now this is all examinable, everything that you see over here. One thing to make note, solids, they can't be compressed. As I told you guys, in reality liquids can be somewhat compressed because their particles, there are some empty spaces in between, but in our syllabus we'll say their volumes are fixed and they can't be compressed, right? So they can't be compressed, as you can see all the details over here. Okay, now this is what we have already discussed. Solids having a fixed shape, volume, vibrate about their fixed positions, particles packed closely together. That is what gives them high density. For liquids, their volume is fixed because the particles are still quite close, not as close as solids, of course, and they have comparatively lesser density than solids, but more density than gases. and the particles over here can slide over each other. That would be the movement over here. For gases, they do not have a fixed volume. You can see there is a lot of empty spaces in between. um, Liquids and gases both would be fluids because they can flow. That is why they take the shape of the container. And since there are a lot of empty spaces in between, so we can actually bring the particles closer together by decreasing the volume, by pushing the sides of the container inwards. And you can see, like, the particles in a gas, they move at extremely high speeds. 500 meters per second is kind of like somewhere closer to 800 1800 1800 kilometers per hour. That is a lot of speed, right? So the particles actually move at very, very high speeds. Okay, now next up, we'll discuss the past papers. Whenever you see this screen, now we'll be discussing past papers, the multiple choice questions, the theory questions related to the concepts that we just discussed. So let us start with the first question. You guys can actually pause the question over here, try it on your own for all these questions, and then maybe unpause the video and look at the explanation. An attempt was made to compress a gas and a solid using the apparatus shown. Which substance would be compressed, and what is the reason for this? So they want us to find like which is compressed and the reason for it as well. First of all, we already discussed solids, liquids can't be compressed. So we can actually cancel out C and D already. Why? Because they have written solid. Solids can't be compressed. Gases can be compressed. Now, as we know, either A or B is the answer. Let's look for the reason. The gas particles are close to each other. Are they? Solids are close to each other, aren't they? Gas particles are actually far apart from each other. Right? Because they are far apart, we can actually bring them closer together. So that is what makes them compressible, right? So we can cancel out A now. B is the correct answer. The gas particles are far apart. That is why we can actually compress them. So over here, the correct answer should be answer B. I hope this made sense. Next question. The diagram shows a cup of tea. Which row describes the water particles in the air above compared with the water particles in the cup? So read this statement carefully. This statement over here. Which row describes the water particles in the air? So basically gaseous particles. We have gas over here. So they are saying these gas particles, compare these gas particles to the liquid particles that we have inside the container. We have these liquid particles inside the container. The reasoning over here would be in reference to these gas particles. So are these gas particles moving faster as compared to the liquid particles? The fastest movement is for gases because they have the highest kinetic energy. Slowest is for solids. So we are talking in terms of the air particles. Are they moving faster? Yes, they are. They should be moving faster because of the highest kinetic energy. So there should be a tick in this particular column, right? Because they are faster. So that way we can cancel out two options C and D. Now, in reference to gas particles, of course, are they closer together? Gas particles are actually furthest apart for all our three states of matter. So they are not close together. There should be a cross in this column. Liquid particles are closer together, right? So you need to read this in terms of gas particles. Are they closer together? Not really. Liquid particles are closer together. So we should have a cross over here. So you can see that make B the correct answer. A is out because tick over here means they are closer together. No, they are not. So the correct answer over here should be. I hope this made sense. Next question. In which substance are the particles close together and slowly moving past each other? So the first thing that we notice, moving, it can't be solids, right? Solids are already out. Solids are out. Why? Because particles in a solid don't really move. They only vibrate about their fixed positions, right? So slowly moving past each other is for liquids, right? For gases, they move around in all directions at very, very fast speeds. And close together, it can't be a gas now. In a gas, the particles are far apart from each other. For solids and liquids, they are actually quite close, but the second statement, slowly moving, cancels out a solid. So it can't be a gas or a solid. It should be a liquid. So in A, we have air, which is a gas, A is out. In B, we have a solid, ice, B is out. In C, we have steam. Steam is also a gas, gaseous state, right? Basically, gaseous state of H2O or water. So C is out as well. We are looking for a liquid. D is water. That makes this the correct answer. Water is a liquid. So liquid, you are looking for a liquid. D is the answer. Next question. The diagram shows the arrangement of particles in three different states of matter of substance X. Just by looking at these diagrams, state 2 particles are furthest apart, so this should be a gas. State 3, regular arrangement, particles very close to each other, should be a solid. And for state 1, this should be a liquid. Particles are quite close, but not as close as a solid, of course. And irregular pattern as compared to solids. Solids, they have a very regular pattern. Which statement about physical states of substance X is correct? Particles in state 1 vibrate about their fixed positions. That would have been for a solid. But is state 1 a solid? Not really. It is a liquid. That cancels out A. State 1 changes to state 2 by diffusion. Changes in state like melting, boiling, condensation, these are changes in state for us. Um, Diffusion is just a physical process when particles basically move from one position to a different position, basically from a region of high concentration to a region of low concentration, which we will discuss in this chapter, um, in this class, inshallah, but not right now. So this is out because diffusion is just physical movement of particles from one region to a different region. That does not, that has nothing to do with changes in state. So B is out. uh, State 1 to state 2, this change in state, this is basically from a liquid to a gaseous state. Liquid to a gaseous state is evaporation or boiling, by the way, just letting you guys know, although that has nothing to do with this question. State 2 changes directly to state 3 by condensation. Now state 2 to state 3, condensation is reverse of boiling. Boiling is from liquid to gas, so this should be from gas to liquid, right? Now state 2 to state 3, this is gas to a solid, right? So not condensation, right? So C is out. The substance in stage 3 has a fixed volume. It is a solid. Solids do have a fixed volume, don't they? It can't be further compressed, right? So this is as close as the particles can get. So D is the actual answer. This statement is correct. Which statement about a solid, liquid, or a gas is correct? A solid has a fixed shape. That is correct. It has a fixed shape and can be compressed. Can it be compressed? No, it can't. It can't be compressed. The reason being the particles are already very close to each other. So this makes this statement incorrect. A liquid takes the shape of the container. Yes, it does. And can be compressed. No, it cannot be compressed because the particles are already quite close to each other. So B is out. A solid has no fixed shape. Solids actually have a fixed shape, so we can just cancel C out already. C is out already because they actually have a fixed shape. D, a gas takes the shape of the container. Yes, it is a fluid, just like liquids, it takes the shape of the container and can be compressed. Yes, it can. It doesn't have a fixed volume. The particles are actually quite far from each other, so gases are compressible. So that makes D the correct answer over here. I hope this made sense. Next question. The arrangement of particles in solids, liquids, and gases are different. Which statement about the molecules in ice? Ice, of course, would be solid. This would be solid. Water would be liquid, and steam would be gas. Is correct. The H2O, basically water particles, water molecules. The H2O molecules are on average closest together in steam. No, they are furthest apart in steam. Closest in solid. That makes A incorrect. The H2O molecules are on average furthest apart in water. Not really. They are furthest apart in a gas. The H2O molecules in steam, so gaseous state, have second highest kinetic and has second highest average velocity. Velocity has everything to do with kinetic energy. For those who are studying physics, basically kinetic energy formula is half mv squared. V is the velocity. So if you have greater velocity, if you have greater kinetic energy, you have greater velocity or speed, right? So the H2O molecules in steam, they have the second highest average velocity. They have the highest kinetic energy, so highest velocity. So not second high. C is out. The H2O molecules in ice solids are able to vibrate. Yes, they are. In solids, the vibration is about there is no movement. They can't move around here and there. They can only vibrate about their fixed positions. So D is the answer. Which statement about liquids and gases is correct? 1 cubic centimeter, this is basically unit of volume, of gas contains more particles than 1 cubic centimeter of a liquid. So in a gas, basically the particles are far apart from each other. For liquids, the particles are actually closer. So if you take the same volume of a gas, liquid, and solids, because the particles are closest together in a solid, there would be greatest number of particles in a solid, and in a gas the particles are actually furthest apart. So in a gas there would be least number of particles, right? And for the liquid there would be somewhere in between uh, gas and solids. So over here they are saying the opposite in A. Gas contains more particles in the same volume. No, it contains less particles in the same volume. That makes A incorrect. A is out. A given mass of a liquid has a fixed volume at room temperature. Now we have already discussed for liquids, do they have a fixed volume? Yes, they do. Solids and liquids, they have a fixed volume. That is why they can't be compressed. B is the actual answer, but we'll still do C and D just to see why they are incorrect. Particles in a liquid can easily be forced together. No, the particles in a liquid are already very close to each other. Of course, not as close as solids, but because they are so close, it is extremely hard for us to bring them closer together. So basically this easily makes this statement incorrect. Can we bring them closer together? Yes, we can, because in solids they are closest, but it's not an easy process. They are already quite close to each other. Particles in a liquid have fixed positions. In a liquid they do not have fixed positions. They have irregular positions, and the particles can actually move around here and there. There is movement. They can slide over one another and move around. So fixed positions would only be for solids. So that makes D incorrect. I hope this made sense. Next question. Which row describes the spacing and arrangement of particles in a solid, a liquid, and a gas? So for solids, they are saying this is only like this is for spacing as well as arrangement, right? This question is for spacing and arrangement. So in solids, they are saying close together and randomly arranged. Are the particles randomly arranged in solids? Not really. They have a fixed pattern, a regular pattern. This random arrangement makes A incorrect. For solids, it should have been regular pattern. So A is already out. We don't have to look at liquid and gas for A. Now for B, close together and randomly arranged. Once again, B is also out. It would either be C or D. For solids, close together and regularly arranged, this is correct. And for D option as well, close together and regular, regularly arranged. Let's have a look at liquids for C and D. Close together, yes. random are they randomly arranged? There is an irregular pattern, there is no regular pattern, so this is actually correct. Let's have a look for this. Regularly arranged, regular arrangement is for solids only, right? That makes this incorrect, so we can already cancel out D now. But let's have a look for gas arrangement as well. Far apart, yes. For gas they are far apart, you can see close together over here, so that makes this incorrect as well. And randomly arranged, yes, they are randomly arranged in gases as well, so that makes C the correct answer over here. C is the answer. Next question. The conical flask contains compound X, which is present in solid, liquid, and gaseous states. Which statement is correct? A gaseous molecule has a lower mass than liquid X molecule. So mass is, this is related to the molar mass. So for example, for H2O, let's just take an example. Hydrogen has a mass of 1, right? We have 2 hydrogens, so 1 multiplied by 2. Plus for oxygen, the mass is actually 16. This is given in the periodic table. So the total here would be 18. Whether we have H2O in a gaseous state, in a solid state, or in a liquid state, this molecule will have this mass. So molecules, they have the same mass. Doesn't really matter in which the particle would have the same mass, whether it is in a solid, liquid, or gaseous state. That doesn't really matter. So A is out. It can't have lower mass because it has the same mass. Energy is released when X changes from liquid to a solid. Let's have a look at option C and D as well. So liquid X is at a higher temperature than solid X. So they are all in the same container, right? They are in the same container. So the temperatures would more or less would be similar, right? Temperatures would be more or less the same. So C is out. Although their energies can be more for gaseous, they do have more energy, and for liquids, they have more energy as compared to solids. D states liquid X molecules, they vibrate about their fixed position. No, that would have been for solids. Now, this is related to changes in state. So, what happens when we, let's say, we take ice from refrigerator and bring it to room temperature. Let's say nowadays room temperature is somewhere close to 20-25 degrees Celsius. When we take it out from the freezer, where the temperature is actually negative, let's say negative 5 or negative 10 degrees Celsius, when we take it out, we put it at room temperature, which is 20 degrees Celsius for us, let's say, it starts melting, right? Why? Because it gains the thermal energy from the surrounding. Basically, it gets warm. So when it is the other way round, basically liquid to solid, it actually loses energy. In case of solid to liquid, it was gaining energy. In case of liquid to solid, which is the opposite process, this is basically freezing or solidification, opposite of melting, which was happening when it was converting from solid to a uh, liquid state. Over here, the energy would actually be released to the surroundings, opposite of absorbing, right? It is released. That is why the liquid particles, they can move around in a confined space. The particles can actually move around here and there, but for solids the energy is so less for the particles that they can only vibrate about their fixed positions, right? So that is why B is the correct answer. Which diagram represents the arrangement of particles in a gas? So we are looking for a gaseous arrangement, so they should be far apart from each other, a lot of empty spaces in between. So D, you can see a very regular arrangement. So this is definitely not a gas. Have a look at B and C. You can see the particles are still quite close to each other. Have a look at A. The particles are far apart from each other, right? So this is the gaseous arrangement. A is the correct answer. Okay, now we'll discuss theory questions of the topics we already discussed. Okay, so now we'll discuss the theory questions related to the concepts that we just discussed. Sulfur is an element in group 6 of the periodic table. Sulfur is a solid at room temperature and pressure. Describe the motion and separation of the particles in a solid sulfur. So, first of all, solid is the keyword, motion, separation. Motion is related to movement. Separation means like how far or whether the particles are close to each other or are they far apart from each other. So, for a solid, the motion actually is vibrates about their fixed positions, right? So, particles they vibrate about fixed positions. Now, as far as separation is concerned, whether the particles are close to each other or far apart, in a solid, the particles are close together. So, you can also say particles are close to each other. Now, next, liquid sulfur reacts with chlorine to produce disulfur dichloride. Describe how the general physical properties of a liquid differ from those of a solid. So, differences between liquids and solids. Give two differences. The first can be like solids, they have a fixed shape, right? Meanwhile, liquids, they don't have a fixed shape. That is why they take the shape of the container. So, solids have a fixed shape. You can also give the reverse logic of this. So, for example, you could have said liquids don't have a fixed shape or they take the shape of the container, unlike solids. That would be reverse logic. So, that would have been marked correct as well. Now, the second difference can be the liquids are fluids, they flow, but the solids can't flow. So, you can say liquid flows, but the solids they don't flow because they are not fluids. Next question. This question is about iron. Iron is extracted from iron ore in a blast furnace. Iron collects at the base of the blast furnace as a liquid. Describe the arrangement and motion of the particles in a liquid. So, once again, liquid over here, that is the key word, and we need to give specific answers related to arrangement and motion now. So, as far as arrangement is concerned, whether the arrangement is regular or irregular, for solids they have a regular arrangement, for liquids and gases irregular. So this is a liquid, so irregular arrangement, or you can just write irregular, that would be marked correct as well. Arrangement is already written. For motion, the whether the particles are moving, and if moving, how. So for liquids, the particles can actually slide over each other or one another. The particles slide over each other. We don't have to specifically write particles because that has already been written for us. Particles in a liquid over here, they can slide over each other.
Assalamu alaikum everyone, welcome to the class. So now we'll move on to the next section. So will be this would be the second lecture of states of matter. Okay, so over here you can see we have changes in states of matter. So over here you can see we have a solid state, liquid state, and gaseous state. Whenever we move from solid to a liquid state, that is known as melting. And a good example would be taking ice out of a freezer. When you take ice out of a freezer at room temperature, let's say the room temperature is around 20ish degrees Celsius, it melts. The ice basically melts, converts from a solid to a liquid state. Now, when we convert a liquid into a gaseous state, that is known as boiling. A good example would be when you make tea, for example, you boil water. When you boil water, some of the particles do get converted from a liquid to a gaseous state, depending on whether the temperature is high enough for those particles. So a conversion from liquid to a gaseous state would be known as boiling. This conversion is also known as evaporation, although there are a few differences between evaporation and boiling, which we'll discuss in a bit. But both these conversions are from liquid to a gaseous state. Reverse of boiling would be known as condensation. That is your conversion from a gaseous to a
liquid state, and reverse of reverse of melting would rather be freezing. Freezing is the reverse of melting. We also sometimes refer to it as solidification. Solidification would also be the same as freezing. So these are some of the conversions which are examinable for you. There is another conversion, although that is quite rare, when solid directly converts into a gas. This is no longer examinable for you, but just as a concept or general knowledge, you should know some of the particles do get converted from solid to a gaseous state. An example would be dry ice. Rather than first converting into liquid, it directly converts into gaseous state. And we also have iodine, which is a volatile substance. Volatile means it has a low melting and boiling point. So those type of substances, they can directly convert into a gaseous state from solid. Okay, now over here in this diagram, you can also see the conversions, which are of course examinable for you. So liquid to a gaseous state, you can say you can see over here evaporation or boiling, and reverse of evaporation or boiling would be condensation. Then we also have melting over here, conversion from solid to a liquid state, and freezing would be reverse of melting. Now sublimation, as you can see the arrowhead going towards gas, rather than converting from solid to liquid first and then to a gas, some substances which are volatile can directly convert from a solid to a gaseous state. Now, as far as energy is concerned, we have already discussed the particles are closest in a solid state and they have high forces of attraction. And the particles, they are furthest away in a gas, but they have the highest kinetic energy. So when we go from solid to a liquid state, for example, that is melting, or from a liquid to a gaseous state, so we are actually going towards higher movement. In solid, for example, we have very little movement, close to no movement. The particles can only vibrate about their fixed positions. But as far as liquid is concerned, the particles can actually slide over one another. Now, from liquid to a gas, it would be sliding over one another to moving at very high speeds in all directions. So you can see both these are concerned with increase in kinetic energy. So when we have increase in kinetic energy, basically we say increasing internal energy. Uh, this internal energy concept is examinable for your physics syllabus. What we mean by internal energy is basically this is combination of two types of energies: kinetic energy plus potential energy. So when the kinetic energy increases, the internal energy also increases. So that would be the case in melting as well as evaporation or boiling. So when we are increasing the energy of particles, when we are giving it heat basically, so in both these changes in states, melting and evaporation, the heat energy, thermal energy would actually be absorbed. And when we have the reverse processes, for example, condensation over here or freezing, these are opposite to boiling or melting. In this case, we are going from comparatively faster movement to comparatively slower movement. So over here, there would be a decrease in internal energy and hence decrease in kinetic energy. So the thermal energy would actually be released into the surroundings in the process of condensation as well as freezing. We also have these heating curves. This is known as a heating curve. In a heating curve, basically we draw a graph and we check what is happening to um, the state of matter and the particles as the temperature increases or as we give it heat. So the horizontal parts of the graph that you see, basically this part over here, this part, and also the parts in between these two uh, points that I have shown over here. So when we have horizontal lines in a heating curve or in a cooling curve, the horizontal lines would tell us that there is a change in state going on over here. And when there is a change in state, the temperature does not increase. So if we go to the left from here, you can see the temperature is constant. We have temperature on the y-axis and heat added, or we can also have time on the x-axis. So as we are giving it heat, during the process, during the change in state, during this horizontal state, the temperature does not change. Why? Because there is a change in state. Whenever there is a change in state, it can be any of the four changes in states that we have in our syllabus. During a change in state, the temperature cannot increase neither decrease. The temperature always remains constant. So let's say this is point A, point B, this is C, D, E, and let's say somewhere around here we have F. So at point A, you can see the temperature is increasing. When we give it heat, temperature increases. At point A, we have a solid state. In a solid state, the particles can only vibrate about their fixed positions. When we have enough energy in the system, basically when the melting point of a substance is reached. So this horizontal state means this must be the melting point of the substance. This temperature must be the melting point of the substance. Melting point is the temperature at which a substance melts. So as soon as the melting point is reached, the temperature becomes horizontal, because at this point the change in state would start. The solid would start converting into a liquid state. So at A we have all solid, so I'll just write S over here, that means all solid. At B we have all solid as well. But when the change in state starts during this horizontal part of the graph, during this phase, this would be a solid plus liquid mixture. This would be solid plus liquid mixture. And as time passes, more and more particles are converting in from solid state to a liquid state. At point C over here, we'll have all liquid. The entire substance would have converted into a liquid, and we'll have a liquid state over here as well. So during this change in state, you can see we have a mixture of a solid and a liquid state. This is basically the melting process as we give it heat, and reverse of it would of course be freezing, but in that case the temperature would be decreasing, not increasing. Over here the temperature is actually increasing, so we are giving it thermal energy. That means it must be the melting process. So why does the temperature not increase or decrease during a change in state? Because the entire all the energy is actually utilized or used to either break the bonds or make the bonds. In this case, in a solid state, the bonds are already quite strong. So what happens over here is the all the energy that we are giving it, all the heat energy, that is actually utilized or converting into uh, the kinetic energy of the particles, and now more and more particles can actually slide over one another rather than just vibrating about their fixed positions. So all the energy that we are giving it, all the thermal energy, is used to convert it into kinetic energy. When the process has ended, when the change in state has been completed, only then the temperature can rise. So at point C onwards, the temperature can rise because the entire substance has converted into a liquid state. Now you can see on this graph, till point D, the temperature is actually increasing. If we go to the left from point D, this point actually, this temperature is the boiling point of the substance. This is the boiling point of the substance. The boiling point would be that temperature at which the substance starts converting from a liquid to a gaseous state. At D, we have all liquid. In between this horizontal state, the horizontal stage of the graph shows that the change in state must be occurring. So over here we have liquid plus gaseous state, a mixture of liquid plus gaseous state. At E, we'll have entire substance would have converted into a gaseous state. And now, as you can see, the temperature starts increasing. Why? Because the entire substance has converted into a gaseous state. This is known as the boiling change in state. You can also call it vaporization. Vaporization is another name for boiling. You can also call it evaporation, but evaporation has a difference, that evaporation does not occur at the boiling point. So the exact name would actually be boiling over here, although the change in state is same for boiling and evaporation, but boiling occurs at a fixed temperature rather than uh, a range of temperature. We'll discuss the difference between the two in a bit. So this is known as a heating curve. The horizontal stages would represent a change in state. So you need to know that the temperature cannot rise or decrease, it stays constant as long as there is a change in state occurring. Now, in our syllabus, we also have a cooling curve. So this is basically the exact same graph, but in reverse, kind of like reverse, uh, um, when our temperature is actually decreasing. So over here, initially, I'll just mark a few points: A, B, C, D, E over here, F, and let's say this is G. Initially, of course, the temperature is still on the y-axis, and on the x-axis we have heat. In this case, the heat is actually released to the surroundings. In the previous curve, the heating curve, we were giving it temperature, we were giving it heat energy. So heat was actually being absorbed, but over here, heat is released to the surroundings. It is given out. So at A, we have a gaseous state, and as more and more heat is removed from the system, at B, this particular temperature, this is condensation, and condensation is reverse of boiling. So this actually would be the condensation point or the boiling point. The condensation point or the boiling point is the same temperature. The only difference being, in boiling point, boiling would occur when the temperature is increasing, condensation would occur when the temperature is decreasing. They occur at the exact same uh, temperature. So for example, boiling point of water is 100 degrees Celsius, condensation point is also 100 degrees Celsius. So at B, at A we'll have all gas, at B we'll have all gas, and in between B and C we have a mixture, gas plus liquid, and at C we have all liquid because condensation is complete now. At D we have liquid, you can see. At E we have all liquid, but in between E and F we have a mixture, liquid plus solid, because next change in state is occurring, freezing, which is reverse of melting for us. So this temperature would actually be the freezing point or the melting point of the substance. Both are the same temperature. So for a freezing point and melting point of water is 0 degrees Celsius. The major difference being, in freezing the temperature keeps on decreasing, in as in we are going, it doesn't decrease when during the change in state. By decreasing, I mean temperature is going down from, let's say, 10 degrees Celsius, and 5, 4, 3, 2, 1, eventually to 0, and then it goes in negative when the entire process of freezing is complete. And in reverse, in melting, the temperature would be increasing. So for example, -4, -3, then eventually reaches 0, then 1, 2, 3 after the process of melting is complete. So that is what I mean by temperature increasing or decreasing. So during the change in state, the freezing, you can see the temperature has become constant. The temperature can neither increase or decrease. At F, we'll have the entire process of freezing is complete, all solid, and now the temperature can decrease. Okay, now this entire, the summary of this all of all these processes. Melting is when solid changes into a liquid state. Of course, it requires kinetic energy. We need to give it heat and the temperature. This process would only occur at a specific temperature, which is known as melting point of that particular substance. Boiling is a process in which liquid converts into a gas. Of course, this would require heat energy being taken in, absorbed, and this will also occur at the exact temperature, the boiling point of the substance. Freezing is reverse of melting. It is a change from a liquid to a solid state. It occurs at the exact temperature. This freezing point and melting point would be the same thing for the substance, and over here the energy would actually be released to the surroundings. Now, evaporation. Now, there are a few differences in boiling and evaporation, although the conversion is the same, liquid to a gaseous state for both. Evaporation occurs at a range of temperatures. So, for example, for water, evaporation can occur at, let's say, 10 degrees Celsius, 15, 20, 40, 50, 60, 90, 95 degrees Celsius. So, evaporation can occur at a range of temperature. But boiling only occurs for water, specifically at 100 degrees Celsius for pure water. So evaporation can occur at a range of temperatures. doesn't have a fixed temperature for evaporation, but for boiling we have a fixed temperature. Another difference is evaporation occurs only at the surface of the liquids. Meanwhile, boiling can occur throughout the liquid. So for evaporation, only those particles which are at the top layer, top surface, they have enough energy to leave. Not even all of those particles have enough energy to leave. Some of those particles at the surface would have enough energy to leave. So evaporation only occurs at the surface of the liquid. Meanwhile, boiling occurs throughout the liquid. Now, evaporation can actually occur at low temperatures as well, which would be below the boiling point of the substance. At boiling point, we'll only have boiling. Now, if you have a larger surface area, there would be more evaporation. But for boiling, it because it occurs throughout the substance, so it doesn't really require specifically a larger surface area. Of course, when there is a larger surface area, or when there are more water particles, there is a good chance of greater boiling as well. But for evaporation, we actually need a larger surface area for there to be greater evaporation. That is why sometimes back in the day, if you talk to your grandparents, um, they used to cool tea by putting it into a container with a larger surface area. And when it was slightly cooler, then they used to put it in mugs to drink. So because larger surface area has more evaporation and the substance cools a lot quicker. Evaporation also has a cooling effect. Now for condensation, this is reverse of boiling. Basically, it occurs at a fixed temperature known as condensation point, and even in this process, this would be reverse of boiling, so energy would be released to the surrounding. Sublimation, as I told you guys, this is no longer examinable, but when a substance directly changes from a solid to a gaseous state, this would be sublimation without it changing into a liquid state. A good example would be iodine or solid carbon dioxide. These are a couple of examples. And of course, reverse of this would be desublimation or deposition. Okay, now when substances are heated, they absorb thermal energy. When they absorb thermal energy, some of that energy can be converted into kinetic energy. So the particles start vibrating more and more. So that is what was happening in the melting as well as condensation phase. When we are giving it heat, what happens? The particles start vibrating more and more, and eventually, let's say it was in a solid state previously, it could only vibrate about with their fixed positions. But when it converts into a liquid state, it can actually move around and slide over one another. So the kinetic energy, which is energy related to movement of an object, basically does increase when we give heat to a substance. So this entire process over here has been written. For example, when we heat a liquid, the liquid can the particles would start vibrating, not vibrating, but actually move around more and more. And eventually, when they have enough energy, they can just move freely in all directions. So in that case, the liquid would have converted into a gaseous state. So we have already discussed heating and cooling curves for these substances, and of course, you need to know that the horizontal sections would be when there is a change in state occurring. Okay, so and this reversible arrow, this means this means going from left to right, and this would mean going from right to left. We'll do a few questions, and then you'll get to know how we solve these questions. But this top one basically means going from this end to this end, and the bottom arrow means going from right to left. So this is the meaning of this arrow. Another concept that you should know, that these horizontal parts of the graph, they can also occur during if we have room temperature, because at room temperature we are not giving it more heat. So horizontal sections can also occur at room temperature. So eventually, let's say there is no change. For example, we take tea. We It is very warm initially, but over time it keeps on cooling down. Eventually, it reaches the room temperature. It will not go below the room temperature now, because we aren't cooling it. We aren't putting it in a freezer, for example. Neither are we heating it. So these horizontal parts can also be due to room temperature. Generally, in most of the cases, it would be because of the change in state. But when we are not increasing or decreasing and we have room temperature, they can also we can also have horizontal parts during room temperature. But at room temperature, of course, the this part of the graph would no longer be required. At room temperature, the temperature does not further decrease or increase, so these parts would not exist when we have room temperature in these graphs. Let's do a few questions and let's see if you guys understood anything. The first question over here: in which changes do the particles move further apart? So from gas to a liquid state, the gas in the gaseous state, the particles are furthest over here, and solid state they are closest, right? So from a gas to a liquid, they are actually moving closest. So W is out, and from a liquid to a solid state, which is X over here, in solid they are closer. They are specifically asking move further apart, right? So we need to specifically give this answer. So even in W as well as X, they are actually moving closer. So you can see in A we have X, as well as W, so this is out. In B we have W as well out, and in C we have X, this is out. From solid to a liquid state, in solid they are closer, the particles are stacked together in a regular pattern. But when they convert into a liquid state, they are further apart. Of course, not too far apart, but still further as compared to a solid. And from liquid to a gaseous state, they move even further apart. So Y and Z is what we were looking for, and that is given in option D. D is the answer. Next question: the diagrams X, Y, and Z represent three states of matter. This would be the solid state, regular pattern. This would be the liquid state, and this would be the gaseous state. Which change occurs during boiling? The boiling is your conversion from liquid to a gaseous state. Liquid to gaseous, that is your boiling. So Y to Z basically, so that makes B the correct answer. Which change in state takes place during evaporation? Once again, liquid to a gaseous state. This is what we are looking for, and liquid to a gaseous state, B is the answer. In which process do particles move closer together? So furthest apart in a gas, comparatively closer in a liquid, closest in a solid. But they specified remain in motion. Are the particles in motion during the solid state? No, they are not. They can only vibrate about their fixed position. They can't move around. So they should be closer together. They should be coming closer together. So the two processes in which the particles come closer together are condensation, gas to a liquid state, and freezing, liquid to a solid state. But in freezing, are they do they remain in motion? Not really. So what we are looking for is condensation. So you can see in A we have condensation. So this would be the answer. The changes that occur when a substance changes state are shown below. Which process W, X, Y, and Z is occurring in the following four situations? Butter melts on a warm day. Butter melts. So in melting, it converts from a solid to a liquid state, right? Solid to a liquid state. So this part should be W. You can see W is going from solid to liquid state. Now next, water condenses on a cold surface. Condensation is from gas to a liquid state. Condensation is from a gas to a liquid state, and gas to a liquid state is Y. So I'll write Y over here. Next, the volume of liquid ethanol in an open beaker reduces. So basically evaporation is occurring. When it reduces, that means some of the particles have converted from a liquid to a gaseous state. So this is going from liquid to gaseous state, and liquid to gaseous state you can see is X. And ice forms inside a freezer. This is solidification or liquid to solid state. Liquid to solid state is actually Z. So let's see, W, and then we have Y for number 2. We can cancel out A as already. You can see these two are already out because they didn't have W. Now A is also out. Just confirming for the next. 3 should be X and last one should be Z. So B is the correct answer. A liquid is heated until it boils. Which result shows that the liquid in the test tube is pure water? So when we have pure substances, they boil. Basically, the change in state would be occurring at a fixed temperature. When it is a mixture, it melts or boils at a range of temperature. So, for example, pure water would not boil at 100 degrees Celsius. Pure water would boil at 100 degrees Celsius, but impure water, I was referring to impure water, it does not boil at 100 degrees Celsius. For example, seawater is impure, so it might boil at 102, 103 degrees Celsius, somewhere in that range. But for pure water, it will always boil at exact temperature 100 degrees Celsius. So this is basically a test for purity as well. So because we are referring to pure water, it will only boil at 100 degrees Celsius. So that is its test. The temperature reads 100 degrees Celsius during the, the boiling state. So you can see a liquid is heated until it boils, right? So during boiling, water should boil at 100 degrees Celsius exactly. Okay, now what are the processes W, X, Y, and Z in the following diagram? So let's start with the W, solid to liquid, melting, liquid to gas, boiling or evaporation. Now Z is your gas to liquid. We are going from right to left now. You can see the direction of the arrow, of course. Now gas to liquid would be opposite to boiling, condensation. And lastly, we have liquid to solid. This would be freezing or solidification, freezing. Let's have a look at the correct option. That shows this C. See, see. You need to see these columns as well, headings. Next, in which changes do the particles move further apart? I think this is practically the same question in we did previously. In solid to a liquid and liquid to a gas, they move further apart. In solid, they are closest. In gas, they are furthest apart. So Y and Z. D is the answer. The three rectangles show the arrangement of particles in each of the three states of matter. X, Y, and Z represent the processes needed to change from one state to another. What are the processes X, Y, and Z? So first of all, this looks like a solid state, regular pattern. This looks like a liquid state, and this looks like a gaseous state. So first of all, X is from liquid to solid. This would be freezing. So X should be freezing. You can see we only have one option. So now we know D is the correct answer, but we'll just confirm. Uh, Now Y is going from a liquid to a gaseous state. Liquid to gaseous state would either be evaporation or boiling. And Z is your conversion from gaseous state to liquid state. This is reverse of evaporation or boiling. So this would be condensation. So D is the correct answer. The diagrams of the three states of matter for carbon dioxide are shown. Which two diagrams show the states of matter before and after sublimation? Although this should no longer be examinable for you, but sublimation is conversion from solid to a gaseous state directly. Solid to a gaseous state directly. Now, uh, I guess we'll just skip this because this is no longer examinable for you from this year onwards. So we can actually skip this one. But if you still wanted to do it, solid to a liquid state, you can see this is solid. The particles regular pattern closest together. This is liquid, some spaces in between. This is gaseous state. So solid to a gaseous state directly would of course be 3 to 1. So C should be the correct answer if you still wanted to know the answer, although this is no longer examinable. The melting points and boiling points of three elements at 1 atm pressure are shown. Separate samples of argon, nitrogen, and oxygen are stored at negative 200 degrees Celsius and at 1 atm pressure. How many samples are liquids? We can make a small kind of like a timeline, and in which I can write the melting point over here and the boiling point over here. Okay, for argon, its melting point is negative 189 degrees Celsius and its boiling point is negative 186 degrees Celsius. So if it is somewhere around here, if the temperature is above 186 for it, so this would be in a gaseous state because it would have boiled. If the temperature is in between 189 and 186, which is between the melting and boiling point, it would be in a liquid state. And if it is below this, like for example negative 190, negative 200, this would be in a solid state, right? In a solid state. So this was for argon only, so I only drew this for argon. So they are asking how many of these would be liquids. So at negative 200, would this be in a liquid state? No, not really, because the temperature of negative 200 comes somewhere around here. It would be in a solid state. So argon is already out. Now I'll draw this for nitrogen. The melting point over here, the boiling point over here. So the melting point negative 210, the boiling point negative 196. So negative 200 is in between. So over here, this would be in a liquid state. As you can see, I already explained. In between liquid, to the right side, it would be in a gaseous state. To the left side, if the temperature is below the melting point, it would be in a solid state. So this is in a liquid state. Lastly, oxygen, the melting point negative 218 and negative 183 is our boiling point. So you can see negative 200 is actually in between these two. So it would also be in a liquid state. So nitrogen and oxygen. So the correct answer should be C. Solid X is heated for 600 seconds. What is the melting point of this substance X? So as I told you guys, this is basically your heating curve. This is your heating curve. So over here we are looking for the melting point. So melting point would be that point where the state is changing. So either it can be this particular point or this particular point. But in a heating curve, we always have melting first and then we have boiling, right? So this would be boiling stage, boiling, and this would be the melting stage. And in a cooling curve, first we have condensation, then we have freezing, right? So we are looking for the melting point. So that would be this temperature. So you can see we have 10 boxes between 100 and 200. Each of them would be 10 degrees Celsius. 110, 20, 30, 40, 50, 60, 170. So this is what we are looking for, B being the correct answer. Substance M is a solid at 30 degrees Celsius. The substance is heated to 80 degrees Celsius and its temperature measured as it cools down to room temperature. The cooling curve has been drawn for us, between which times is the substance M freezing. So as I told you, in this specifically told us as it cools down to room temperature. When I was explaining the concepts, I told you the horizontal part can be due to uh, room temperature as well as changes in state, of course. And when it stops, that means it is definitely due to when the graph stops. So it stops here, right? It doesn't cool further. That means this is not a change in state. This must be due to room temperature. This specifically told us cools to room temperature. So ST is actually our room temperature. This is not a change in state. This is not a change in state. I'll go back to the notes part, just to let you guys know that during our cooling curve, you can see it did go down after this change in state, right? After freezing, it did go down, but the temperature did go down. But over here, you can see the temperature did not decrease. That means this was the room temperature. We only have one change in state over here, and that change in state must be Q to R. So this is where the temperature is changing in between Q and R. This is our only change in state
for this particular diagram. So this must be the freezing part. Q and R, Q to R, B is the correct answer. I hope this made sense. Next question then. A gaseous substance is slowly cooled and temperature recorded every second. This is a cooling curve. The results are shown on the graph. At which point is the substance a solid? At which point is this substance in a solid state? So they specifically told us gaseous substance is slowly cooled. So at A, it must have been in a gaseous state. And when it is in a gaseous state, the first horizontal part for the cooling curve would be condensation. So this would be a mixture of gas plus liquid. At this particular point, all liquid. And at this point, we'll have liquid as well. At C, we have a liquid. And this is the freezing stage. This is the freezing stage. And when we have the second horizontal part of this graph, that means during this change, during this horizontal part, we have freezing that is taking place. So there is a mixture of solid plus liquid, liquid plus solid over here. So you can see at D will have the solid state. At A we have gas. At B, mixture of gas plus liquid. At C, all liquid. D, mixture of liquid plus solid, and we'll have a mixture of like some liquid as well as solid particles. So the only place we can possibly have a solid particle would be at D. The diagram shows changes of state between a solid, liquid, and a gas, in which changes of state is energy being given out. So energy taken in is in melting state as well as in boiling. The reverse of these two processes, condensation and freezing, energy is actually given out. So first of all, liquid, um, solid to a liquid state, this would be melting, energy taken in. Next, liquid to a gas state, boiling, energy taken in again. Reverse of boiling, condensation, energy given out or released. And next up, liquid to solid state, this is freezing or solidification, and in freezing, energy is also given out, it is released. So 3 and 4 is what we're looking for, D. Next question, the table gives data about 4 substances. Which substance has particles in a disorderly arrangement at room temperature? In a disorderly arrangement at a room temperature. Now maybe we can take room temperature at somewhere around 20 degrees Celsius, which is the standard room temperature throughout the world, like average room temperature you can say. Not standard, as in different countries can have different room temperatures depending on um, the season as well as the place they're lying on the hemisphere. So around 20ish degrees Celsius we can take an average room temperature. So disorderly arrangement. So first of all, in A, will this graph, we place the melting point first, minus 114 and minus 80. So any temperature that is below the melting point, this is the melting point of course, and this is the boiling point. Any temperature that is below should be solid. Anywhere temperature in between would be a liquid, and over here we'll have a gaseous state. And this is disorderly arrangement, no orderly arrangement for us. So it should be in a gaseous state. And you can see 20 degrees Celsius is actually greater than the negative 20 boiling point over here. So this should be the correct answer for us. So we'll just mark A as the correct answer. You can see for this and this, 20 degree actually is below this. So solid, 20 degrees Celsius would be below the melting point here as well. All of these are solid, and that would be a regular arrangement. This orderly arrangement can be a liquid as well, because regular arrangement would only be for a solid. In which conversion do H2O, basically water molecules, lose speed? They lose speed. So first of all, ice to water. In ice or in a solid state, they will be slowest, fastest in a gaseous state. So in liquid, like solid to liquid, they actually get faster. They do not lose speed, air is out. Once again, ice to steam, this would be converting into a gaseous state, which is the fastest. Is out as well. Next, steam to ice, gas to a solid state. In a solid state, they can only vibrate about their fixed position. Meanwhile, in a gaseous state, they can move randomly in all directions. So this is the correct answer. They actually lose speed over here. Liquid to gas, in gas they are faster. C is the answer. Okay, let's attempt a few structured questions. Bromine is a liquid at room temperature. State two general properties of a liquid. So one of the properties we already discussed. They take the shape of the container. Of container. Taken. That is, they don't have a fixed shape. Next, maybe we can say they have a fixed volume. Again, maybe you could have said it is a fluid. That could have been another valid point. That is, it flows over the surface or whatever. It's something in that on those lines. Name the changes of physical states A and B. A is going from liquid to a solid state. Basically, this is solidification or freezing. So this would be freezing. Next, B is from liquid to a gaseous state. This would practically be either boiling or evaporation. So I'll just call it boiling. You can state evaporation as well because that is the same change in state. So next, the changes of state of lead are shown. Name the changes of state represented by A. Liquid to a solid state, once again freezing. Practically the same question with different wording. A liquid to a gas. This would be boiling or evaporation. Next, use the kinetic model to describe the differences between liquid lead and gaseous lead in terms of separation between the particles. In a liquid state, the particles are actually closer together. Basically, separation means how far the particles are to each other. Closer together in a liquid state. Right, so as compared to, they are closer together in a liquid state, and we can state far apart. This is what 4 marks, so detailed answer. In a gaseous state. Next, the motion of particles, their movement basically. So for a liquid, particles can slide over one another. Particles in liquid can slide over each other. And for a gas, they move freely in all directions. Next question. Name each of the numbered physical changes shown in figure 1.1. The number one is going from a solid to a liquid state. Solid to a liquid is known as melting. Next, number two is from gaseous state to a liquid state. Gaseous to a liquid state is condensation, right? Next, number three is from liquid to a solid state. Liquid to solid state is freezing. Lastly, Number 4 is liquid to a gaseous state. Either you can call it boiling or you can call it evaporation as well. It's up to you. Both would be marked correct. One difference between boiling and evaporation is the rate at which the processes occur. State one other difference between boiling and evaporation. Boiling occurs at a fixed or specific temperature. Another change could be evaporation only occurs at the surface of the liquid, unlike boiling, which occurs throughout the liquid. So, one of those changes could be boiling occurs at a specific temperature, known as the boiling point. Reverse argument would have been correct as well. For example, evaporation occurs at a temperature below the boiling point, that is, it doesn't occur at a fixed temperature. Another possible reason could have been like you could have stated evaporation only takes place at the surface of the liquid. Evaporation only takes place at surface of the liquid. This would have been marked correct as well. Describe the separation, arrangement, and motion of particles in element X in a solid state. So we need to describe the solid state separation first. They are touching each other or they are close to each other. So we can just say touching each other. The arrangement is a regular pattern, regular arrangement. So we'll just say regular pattern. Motion, vibration about their fixed positions. Vibration about fixed positions. Okay, so now we'll move on to the next section, which is the third section of this chapter, states of matter. So pressure and temperature in gases. So you need to know a couple of relationships of pressure with temperature as well as volume, and temperature with volume as well. This is examinable for chemistry as well as physics. So pressure has a direct relationship with temperature. This means direct relationship when both things are in the numerator. Pressure has an inverse relationship with volume, and temperature and volume, they have a direct relationship with each other. Now, what do we mean by direct or inverse relationship? A direct relationship means when one thing increases, that causes an increase in the other value as well. So if the temperature increases, so like for pressure and temperature relationship, when temperature increases, that would cause an increase in pressure, and when temperature decreases, that would cause a decrease in pressure as well. So whatever happens to one of these values, the same thing would happen to the other as well. This is the meaning of direct relationship. Now pressure and volume, when one thing is in the numerator, the other in the denominator, that gives us an inverse relationship. An increase in one causes a decrease in the other, and vice versa. So if the volume increases, that would cause a decrease in pressure. Opposite. Now if the volume decreases, that would cause an increase in pressure. As far as temperature and volume is concerned, this is also a direct relationship. Increase in volume would cause an increase in temperature, and similarly, a decrease in volume would cause decrease in temperature. We'll discuss all these relationships in more detail now on the next slides. But for now, all these three relationships are examinable. That the pressure temperature relationship is direct, temperature volume relationship is direct, pressure volume relationship is inverse. I'll explain the logic behind all this on the next few slides. So first of all, the pressure is caused by these particles, the enlarged particles. These are basically particles of a substance. This is in a gaseous state. That is why there are a lot of empty spaces in between. Whenever these particles would hit these walls of the container, the pressure would be caused. So although you don't really need to know this for chemistry, but you do need to know this for physics. Pressure has a formula, force over area. So whenever force is caused on a given area, pressure would be caused. So let's say this particle, I can just name it particle A, let's say. This particle A, when it hits this wall, this part of the wall of the container, it, because it's moving, it would cause a certain force on the wall of the container, and this is force caused on a given area, on a given area, a small area over here. So pressure would be caused. If we increase the number of collisions with the walls of the container, the pressure would increase. If we decrease the number of collisions with the wall of the container, the pressure would decrease. So keep this in mind, pressure has everything to do with collisions with the walls of the container. So when I increase my temperature, we discussed on the previous slide, pressure has a direct relationship to temperature. So when I increase the temperature over here, let's say I'm giving heat over here. So when I give heat, the temperature increases. Temperature would increase. That would increase the kinetic energy of the particles. K dot E means kinetic energy of the particles would increase. They'll The speed of these particles increases. Speed increases because kinetic energy formula, although you don't really need to know this for chemistry, but you do need to know this for physics, half mv squared. So kinetic energy and velocity, they have a direct relationship. So when we increase the kinetic energy, the speed of the particles increases. When the speed of the particles increases, more collisions would be caused with the walls of the container. More collisions with walls, and that leads to pressure increasing. The reverse logic would be true as well. So for example, if I decrease the temperature, the kinetic energy decreases, the speed of particles decreases, less collisions with the walls of the container in that case, and the pressure decreases. So you need to know that pressure has a direct relationship to temperature. An increase in one would cause an increase in the other. So over here you can see a relationship of temperature and volume. So pressure, as we discussed on the previous slide, it has a direct relationship with temperature, and temperature and volume, they have a direct relationship as well. Direct relationship, of course, would mean an increase in one would cause an increase in the other as well. So volume is the space occupied by an object. So if you have a bigger space in an object, that would mean the volume has increased. So over here you can see we are giving heat over here. So we are increasing the temperature basically. When you increase the temperature, these particles inside this container over here, these particles, they would hit the walls of this container more and more. When they hit the walls of this container more and more, as long as the thing is expandable, if they kind of like a piston, for example, which can expand, which can be pushed around, so this would be a flexible substance. This would cause an increase in the volume. So the walls of the container, when force is applied by these particles, when they hit these walls more and more, it would expand. So initially my temperature, I increased it, that caused an increase in the volume due to collisions with the walls of the container. So it has something to do with density as well, but that is for physics basically. Density, this has this symbol, is equal to mass over volume, and they have a they have an inverse relationship, the density and volume. But for chemistry, you don't really need to know too much details related to the density. You just need to know this relationship, that temperature and volume, they have a direct relationship. Okay, now pressure and volume, they have an inverse relationship. An increase in one would cause a decrease in the other. So this pump, for example, when we push it outwards, when we pull this pump upwards, when we pull it upwards, the volume increases. The volume would increase, but the number of particles inside this container are exactly the same. So for example, let's say we have these particles, these three particles. Initially, let's say the wall was somewhere around here. Initially the wall was somewhere around here. Now this particle over here had to travel this distance to hit this side of the wall, for example. So this is a shorter distance. When I pull this upwards, I increased my volume basically. When I pull this upwards, the bar or this top part has moved over here, let's say. Now, this same particle actually needs to travel a greater distance, let's say this distance, because it has to travel greater distance to hit this wall of the container. On average, when more distance is required, when the distance between the walls of the container increases, the number of collisions with the walls would also decrease, because the distance on average for these particles to move has increased to hit the walls of the container. So initially I increased my volume. When I increased my volume, the collisions with the walls of the container would become lesser. When collisions with the wall of the container becomes lesser, the pressure actually decreases. So I'll write this down over here. Increase in volume, let's say increases. Average distance, the number of particles are remaining the same either way, before and after. Average distance between particles and the wall and walls increase. When this decreases, when this increases rather, when the distance increases, fewer collisions with the walls of the container. And when we have fewer collisions with the walls of the container, pressure decreases. So you can see I increased my volume, and at the end my pressure decreased. So inverse relationship, an increase in one caused a decrease in the other. And reverse logic would be true as well. Volume decreases, average distance between particles would also decrease. When the average distance between the particles and the walls decreases, there would be more collisions with the walls of the container, and hence pressure would increase. So you need to know all these concepts. Okay, so a good example has been given over here. Let's say I push this inwards. Initially, my volume was high, the number of particles are same. I have decreased my volume. Volume decreases. When volume decreases, let's say I have this particular particle, I'll call this A over here, and let's say this is my particle, same particle. Initially, it had to travel this distance to hit, let's say, this part of the wall. Now it has to travel lesser distance to hit the wall. Let's say this is 7 centimeter, and this is 3 centimeters now. When lesser distance has to be covered, the speed is remaining the same, because speed is dependent on the kinetic energy of the particles. We aren't giving it heat, so temperature is not affected over here. Whenever we check relationship of two things, everything else remains constant. So when we are discussing the pressure and volume, temperature would remain constant. So temperature is constant, speed of particles would be constant. When you have to travel lesser distance at the same speed, you cover that lesser distance faster. So over here, when volume decreased for A, it had to travel lesser distance to hit this piston or the top part over here. So when it had to travel lesser distance at the same speed, the number of collisions with the walls of the container would increase. When the number of collisions on average increases, that would cause an increase in pressure. So pressure increases. So this is the concept behind all this. Okay, so now that we have discussed these concepts related to pressure, volume, and temperature, now we'll try to do a few questions. A gas is placed in a sealed container. The gas has a pressure of 1 atmosphere and temperature of 50 degrees Celsius. It is heated to 100 degrees Celsius. Now we have increased the temperature. Increase in temperature. So there is an increase in temperature now. Uh, and pressure and temperature, they have a direct relationship, right? Pressure and temperature, they have a direct relationship. Now, which row describes the cause of the pressure of the gas and the effect of increasing the temperature of this gas? So, increase in temperature would actually cause increase in pressure, right? Okay, now let's discuss all these options. Option number A, cause of gas pressure, collision between the gas particles. No, collision of the particles with the walls of the container, right? So A is already out. And in B, you can see collisions between gas particles. Not really. It has to be collisions between the gas particles and the container, wall of the container, right? Either C or D is the correct answer. A and B are already out. Now, the effect of increased temperature of the gas. So now the particles will actually start moving faster because temperature increases, kinetic energy increases, speed of particles increases. So every speed of the particles increases. That is what causes greater number of collisions with the wall of the container, and that is what increases the pressure for us. So D has to be the actual answer. Over here, they are saying collisions between become less frequent. No, they would become more frequent. When temperature increases, speed of particles would increase, more collisions with the wall of the container. So that cancels out. See over here, D is the answer. Next, which statement is not correct? They have emboldened not. So whichever is a correct statement, we can actually cancel it out. A, energy is released when a liquid changes into a solid. So liquid to solid, this is freezing, and in freezing we actually need to cool things down, right? So the energy is actually released. In freezing it is released. In melting, which is reverse of freezing, it would be absorbed. So this is a correct statement. We were looking for not correct, so we have to cancel out the correct statements. In option B over here, particles move faster in a gaseous state than in a liquid state. Correct statement. So we need to cancel it out, looking for a not correct statement. C, the carbon atoms in gaseous methane are further apart than in a solid diamond. Yes, in a solid state, the particles are touching each other closer together. In gaseous state, they are further apart. This is a correct statement. We need to cancel it out. We definitely know that D is the correct answer, but let's read the statement. There is a large decrease in volume of a solid metal when pressure is applied to it. Pressure has an inverse relationship to volume. So over here they are saying the there is a large decrease in volume. A decrease in volume would be due to increase in pressure, inverse relationship. When pressure is applied to it, you can see when we increase pressure, the volume decreases. Inverse relationship, D is the correct answer. Next question. Which change in conditions increases the energy of the particles? Increases the energy of the particles. That would be due to temperature, basically. Kinetic energy is related to temperature, neither related to pressure or volume. Volume is just space occupied by an object. Pressure is due to collisions with the walls of the container. So over here you can see increase in temperature over here. An increase in temperature causes increase in kinetic energy, and increase in kinetic energy of course would lead to these particles moving faster. So C has to be the correct answer. Increase in energy would be due to increase in temperature. Okay, now let's do a few theory questions as well. Figure 4.1 shows a gas syringe that contains 60 cubic centimeter of ethene gas. State how the volume of ethene in the gas syringe changes when temperature is decreased. So volume relationship with temperature, temperature and volume, they have a direct relationship. So over here they are saying show how the volume of ethene in the gas range changes when temperature is decreased. So when we decrease the temperature, the volume has to decrease as well. Direct relationship. So we can write volume decreases. Next question. Describe the liquid bromine and liquid gas in terms of arrangement and motion of the particles. So liquid bromine, the arrangement in liquid and gas is irregular arrangement. So I can just write irregular arrangement. Regular arrangement is for solids. Okay, now motion, the particles can slide over one another. Moving particles, basically moving and slide over each other. Okay, next, bromine gas particles, so irregular in this as well, irregular pattern, and the motion freely moving in all directions, fast movement everywhere, everywhere. A sealed gas range contains 80 cubic centimeter of bromine gas. State how decreasing the pressure affect the volume. So first of all, pressure and volume, they have an inverse relationship as we have already discussed. So inverse relationship, they were specifically saying decrease in pressure. So when we decrease the pressure, the volume should actually increase. The volume of bromine gas in the gas range when the temperature remains constant. Everything else, as I told you, should remain constant when we are discussing relationship. So over here, volume should increase because we are decreasing the pressure because of inverse relationship. So we can write volume decreases, or volume increases rather. Sorry. because pressure is decreasing, so volume should increase. So volume increases. Okay, next up. Um Now we have the graph of how the volume of a sample of gas changes when the temperature increases. Basically, we have two types of graphs. This graph is a direct relationship graph, and an inverse relationship graph looks like this. This is an inverse relationship graph. So over here we see a direct relationship, and we all already know the volume and temperature. They actually do have a direct relationship. They do have a direct relationship. Describe how the volume of gas G changes as the temperature increases. So we are increasing the temperature. That should cause an increase in volume as well. Increase in temperature causes an increase in volume. So we can write volume increases. Describe the arrangement and separation of particles in a gas. Irregular arrangement. Separation, like how far the particles are to each other. Separation, they are far apart. Particles far apart. Okay, so now we'll start the fourth and the last section of this chapter, states of matter of chemistry. So the last section is related to diffusion. So diffusion is a process. This concept is in your biology syllabus as well. This is movement of particles from a region of high concentration to a region of low concentration. Basically, this happens down a concentration gradient. When we say from high to low concentration, we mean from a region down a concentration gradient basically. This would only occur in fluids. Diffusion is a process that is only for fluids, because in a solid state particles can't really move, they can only vibrate about their fixed positions. So by fluids, what do I mean? Fluids would represent liquids plus gases. Now, anything that flows basically would be a fluid, and solids cannot flow. So, this is a process that only occurs in fluids. And because the movement is faster in a gas, the particles are faster moving in a gaseous state. So, diffusion would also be faster in a gas as compared to liquid. And diffusion is affected by a few things, for example, mass, temperature, state of matter. We'll discuss those in a bit. So, a good example over here, potassium manganate. You can see these crystals are purplish in color, and over here we have potassium manganate crystals, and they are in higher concentration over here. So, over time, what would happen over here is these particles would move into this region, this region, this region, because they are in lower concentration over here. And similarly, water particles are higher in concentration over here as compared to, let's say, somewhere around here. So these water particles would move towards this side from a region of high concentration to a region of low concentration. So as time passes, this purplish color that you see over here, this would become lighter and lighter because these particles would spread around. Uh, these purplish particles that you see, they'll have a mix of some water particles in between them. This is diffusion, movement of particles from a high concentration to a low concentration, and this works both ways, for water particles to this region over here, or from potassium manganate particles to the surrounding water particles. So you see over time these this purplish color becomes lighter and lighter as the particles spread around, and eventually if we give it enough time, there would be an even distribution of water and potassium manganate particles, and this color would become uniform. So you can see after 4ish hours, uniform color, and this color is lighter as compared to the initial potassium manganate particles that we had. So diffusion is movement from a region of high concentration to a region of low concentration down a concentration gradient. This happens because of the kinetic particle theory, of course, that particles would always be in a random motion, especially for gaseous particles, because they can move at very high speeds in all directions. So this is the summary. This happens due to random movement of particles. So this is a concept that can come in your exam. Which two processes must happen to spread the sugar evenly in the tea? As we just discussed, the even or uniform spread of the particles is primarily due to diffusion. But the sugar over here is in a solid state. As we discussed, diffusion is movement of particles. In a solid state, the particles can only vibrate about their fixed positions. They cannot move around. So first, it has to convert in a fluid state. So this will first dissolve. This would be the first process, dissolving. The sugar first dissolves so that it converts into a liquid state. Now it is a fluid. After that, diffusion can occur. So the first process would always be, in this case, solid conversion into a liquid state or a fluid state. Only then the diffusion can take place. Okay, now diffusion is related to multiple things. One of those things is molecular mass of a substance. When you have lower molecular mass, the the gases, especially we are discussing fluids over here, but primarily gases now, they would when the molecular mass is lower, it they would be lighter basically. So when they are lighter, it's easier for them to move around. So the lighter gas would move faster because it has lesser mass. It is easier for it to move around. This is related to the inertia concept as well for physics. When you have more mass, it makes it harder for that object to move around, to change direction, uh, to accelerate or decelerate. So even in this case, when you have lighter gases, it is easier for those gases to move around. And when you have heavier gases, for example, carbon dioxide is a heavy gas, or chlorine is a heavy gas. So those gases would move slower as compared to, let's say, hydrogen gas, that is a lighter gas. So one of the things diffusion is related to, especially for gases, would be its relative molecular mass. Now, how do we calculate the relative molecular mass? So ammonia, for example, is NH3. What that means is it has one nitrogen. N is a symbol of nitrogen. H is a symbol for hydrogen. And you see this three down here. This means we have three hydrogens. So from the periodic table, first we check the mass of nitrogen. You see, the bigger number would be the mass number, by the way. The smaller numbers that you see, for example, for carbon, the smaller number is 6. You see over here, smaller number is 6, and the bigger number is 12. Masses are the bigger numbers. So the mass numbers are written at the bottom of this particular periodic table. So for example, mass of neon would be 20. So nitrogen has a mass of 14, you can see over here, and we had hydrogen as well. So hydrogen has a mass of 1. So we have one nitrogen which has a mass of 14 and three hydrogens. Each hydrogen has a mass of 1. So this would be 3 times 1 is equal to 3. So the total here would become 14 plus 3 is equal to 17. This is the mass of ammonia. So for example, if I want to find the mass of HCl, hydrogen, of course, we just looked at its mass 1, and we have chlorine. Cl is chlorine. You see 35.5. 35.5. So this would become 1 plus 35.5 is equal to 36.5. So you see, this is comparatively heavier. HCl is heavier, so this will actually move slower. Comparatively, this would be slower, and ammonia, because it is lighter as compared to HCl, this would be faster. So one of the things that affects the rate of diffusion, the speed of diffusion, would be its molecular mass. The lighter gases move faster, the heavier gases move slower, and we can check the masses from this particular periodic table. So for example, if you have O2, oxygen, 2 molecules of oxygen, you see mass is 16, so this would be 16 times 2 is equal to 32. And you should also know that the gases, apart from this group number 8 that you see over here, this is group number 8, all these gases, these would be monatomic. Monatomic means that they have a single molecule. So helium, neon, argon, krypton, these would be monatomic. But the other gases, for example, fluorine that we have, oxygen, nitrogen, even chlorine, these gases would be diatomic, like O2, N2, F2, Cl2 in this form. So let's move on to this example over here. You see the ammonia over here, and ammonia has a mass of 17. Meanwhile, HCl has a mass of around 36.5 ish. Uh, we have taken 36.6 to be precise over here. So now we know ammonia would be faster. Periodic table would be given to you in your exam because it is a lighter gas, and HCl would be slower. Now, where would they react? Where would the reaction take place? Now, you can see these particles, they are moving towards this side, and these particles are moving to the right side over here. But because these red particles, the ammonia particles, are faster, at the same time, they'll travel further towards HCl. So the reaction is likely to place somewhere around here. Why somewhere around here? Because ammonia is faster, it travels more distance in the same time, and HCl is slower, it travels less distance in the same time. So the reaction would take place closer to the heavier gas, HCl in this case. So you can see at the end the reaction actually takes place somewhere around here. When we have two gases which have the same mass, the reaction would take place somewhere in the middle, right? If you have a heavier gas on the left, it would take place somewhere around here, like nearer to the heavier gas in that case, right? Nearer to the heavier gas, further away from the lighter gas. Okay. Another thing that affects diffusion, as I told you guys, was temperature as well. When you have greater temperature, if temperature is greater, the particles move faster, and this is movement related to diffusion is actually related to movement of particles. So if you have higher temperature, the diffusion rate would also be faster because the particles would be moving faster. So now we'll move on to past paper questions related to diffusion. Now, the first question over here: a sugar cube is dropped into a hot cup of tea. The tea is not stirred. We don't mix it. Which statement explains why the tea becomes sweet? The first one: the heated water molecules penetrate the sugar cube. It sweeter because the sugar must have dissolved first, and then there would have been diffusion taking place, right, as we discussed earlier during the concepts. So over here the actual answer should be C. The sugar cube dissolves and its molecules diffuse, but they spread around, and there would be more or less even distribution of sweetness throughout, as long as the entire thing has dissolved and you have given it enough time for it to dissolve, of course. So C has to be the answer. The sugar cube dissolves and its molecules diffuse. A crystal of purple potassium manganate was added to each of the beakers shown in the diagram. One beaker contained hot water and the other beaker contained cold water. In both beakers, the purple color of potassium manganate spreads out, which result and explanation is correct. Now, because in hot water diffusion would be faster because the particles are moving faster, so the color should spread faster in hot water. In A, they are saying faster in cold water. No, that should not be the case. So we can cancel out A and B already. Either C or D is the correct answer. Now have a look at explanation. Particles move faster at high temperature. Yes, they do. So C is the actual answer. Let's have a look at D. Particles move slower at high temperature. Not really. Increase in temperature would increase the speed of particles, so they basically move faster. So C has to be the answer. Which statement is an example of diffusion? So diffusion has many different examples, basically spread of particles from a region of high concentration to a low concentration. Now, how do you smell the food cooking in the kitchen? Basically, this is related to diffusion. The gaseous particles move around, and let's say they spread to the living area or drawing room or your bedroom. You can smell the food. Why? Because of diffusion. And even the perfumes that we put on, it spreads out due to diffusion. So let's have a look at the options. A kitchen towel soaks up some spilt milk. Not really. Soaking up is has nothing to do with diffusion. It should be movement of particles from high concentration to low concentration. Once again, ice cream melts. This is just a change in state, nothing to do with diffusion. Pollen from flowers is blown by the wind. This has nothing to do with diffusion. This is not movement on its own. This is spread due to the wind. The smell of cooking spreading out throughout the house. Yes, this has to be the answer. D. Next, a few drops of perfume were spilled on the floor. A few minutes later, the perfume could be smelled a few meters away. Which two processes had taken place? So, because this is perfume, it spreads out throughout the room due to it being gaseous instead. Now, liquids they don't like spread around very easily. They remain in their position. For liquids, the movement is actually only sliding over one another and remaining in the confined space of the liquid, right? But gaseous they can move around in all directions. So this the perfume smell actually spreads due to it being converted into a gaseous state. So evaporation has to take place. These particles convert into a gaseous state from a liquid state. Now, next, spreading out would be due to diffusion. So D has to be the correct answer. The diagram shows the result of dropping a purple crystal into water. Which two processes take place in this experiment? Now, diffusion is only spreading out of substances. So it is not a chemical reaction, as in they don't react together to form a new substance. It's just they mix together. So it is only a physical process. Because diffusion is a physical process, so chemical reaction should not have a tick around it. So A and B are already out. Now over here, it has to dissolve first and then it diffuses, because solids cannot diffuse. So both diffusing and dissolving should have a tick in front of it. So you can see D has to be the correct answer in this case. Two gas jars each contain a different gas. The gas jars are connected and the cover slips are removed. The diagram shows what happens to the particles of these gases. So this spreading out, even distribution is definitely due to diffusion. So C has to be the correct answer. Next up, which statement explains why the bromine and air mix together? Now, diffusion takes place because of random movement, basically due to kinetic particle theory. This is due to random movement of molecules, gaseous molecules in this case. Bromine and air both are in gaseous state. Random movement of particles, they basically spread around. And eventually, there would be even distribution, like when there is movement of particles from a region of high concentration to low concentration. Now, A states bromine is denser than air. It has nothing to do with the diffusion or spreading out. Whether it is denser or less dense, they would spread out. So we see evenly spreading out. So this is definitely diffusion. Similarly, B is out as well. Bromine molecules moved upwards and molecules in air moved downwards. Yes, but it isn't as if all the air molecules move downwards and all the bromine molecules moved upwards. In that case, we'll have all air over here and all bromine over here. Some particles from down here move up, as well as some particles from up there move down here as well. So there is a good mix of particles. Not all the particles move up and down. They move randomly in all directions, up, down, left, right. So D has to be the answer. Molecules in bromine and air moved randomly. That is what caused spreading of these particles due to kinetic particle theory. Particles moving very slowly, there is movement. So when there is movement, either it should be a liquid state or a gaseous state. In solids, they can't move. Solid is already out. We'll just cross solid slowly. So if they're moving slowly, that means it must be liquid, because in a gas they are moving very fast from area of high concentration to an area of low concentration. So this must be related to diffusion. So let's have a look. A is a change in state, freezing. B is a change in state, nothing to do with diffusion. A substance is diffusing, yes, through a liquid. Why? Because of slower movement. If it was faster movement, in that case, it could have been air as well. But very slowly means it is definitely not air or gas, it is liquid. C has to be the answer. Which diagram shows the process of diffusion? We just need spreading out of substances. So over here, you can see this is a chemical change. You have two black
colored atoms over here, two white colored, and over here you see black and white, they have chemically combined together. So we actually have a different substance over here. This is a chemical process. So A is out. Similarly, in B, you can see we have multicolored molecules, and over here, unicolored. Basically, they have convert. This is a chemical process, so B is out as well. In diffusion, diffusion is not a chemical process. It is actually a physical process in which the particles just they spread around. This is a physical process, not a chemical process. So now either C or D is the correct answer. Let's have a look. Yes, this you can see these there were all white molecules on this side, all black at not molecules, atoms basically, and over here they have spread around. So this is basically diffusion. Let's have a look at D. So once again, this is a chemical change, so we'll cancel it out. We had atoms over here and molecules over here. Aqueous lead nitrate and aqueous potassium iodide are added to a dish containing water as shown. A yellow precipitate forms after a few minutes. Which process occurs before this precipitate forms? Of course, this would spread out. Because this is spreading out, this would be movement of particles from a region of high concentration. Basically, from this yellow region, they will move around and spread even if we give it enough time. So this would definitely be diffusion. Is the answer. The diagram shows how the molecules in the exhaust gases diffuse into the air. Which statement describes what happens to these molecules next? Um, so these molecules would actually spread around. You can see all these black colored atoms or molecules. They'll basically spread around because there is high concentration over here. So you can see there is a more even concentration now. So this is definitely diffusion. So diffusion occurs because of random movement of particles in a gaseous state, especially over here, and they spread around. So we need to look at any option that shows diffusion. The molecules fall to the ground, not really. This has something to do with diffusion. The molecules go back together as they go, not really. The molecules spread further into the air. Yes, they spread and go from high concentration to low concentration, even spread. The molecules stay where they are, not really. They have to move around for there to be diffusion, which we can clearly see over here. C is the answer. The diagram shows the result of dropping purple crystal into water. Which processes take place in this experiment? This is similar to one of the previous questions. This is diffusion, so cross should be in front of the chemical process, and both diffusion and dissolving needs to take place, because in solids, which we have purple crystal over here, in solids diffusion cannot take place. D is the answer. Next, uh, mineral soaked mineral wool soaked in aqueous ammonia is placed in the apparatus shown. After 5 minutes, the damp red litmus paper turns blue. Which process led to this change? So basically, ammonia moved around and reached this point over here. That is what changed the color. So this must be related to diffusion, movement from a high concentration of ammonia over here to low concentration of ammonia over here. So this is spreading out of these ammonia particles, which it should be diffusion. C has to be the answer. Which statements about diffusion are correct? Now, aqueous ions cannot diffuse in water. We have these ions, these are aqueous, so because they must be in a liquid state, so they can diffuse. They are looking for a correct statement. One is already out. A diffusion is caused by random movement of particles. Yes, kinetic particle theory. This is correct. Particles spread out in all directions in diffusion. Yes, they spread evenly in all directions, left, right, up, down, in all directions. So this is correct as well. Diffusion can only take place in solids and liquids. No, in solids they cannot take place. This is incorrect. So 2 and 3. C has to be the correct answer. Okay, which gas has the fastest rate of diffusion? So over here we actually need to find its MR, molecular mass. So let's have a look. We have argon over here. It's the bigger number is the mass number. This is argon 40. So I'll just write it over here 40. C2 and H6. C is over here 12, and we have 2 C. So 2 times 12 should be 24, and we have 6 over here as well. You can see each hydrogen has 1, so this would be 1 times 6 is equal to 6. So the total should be 24 plus 6, 30. HCl, we already calculated it when we were doing the concepts. Hydrogen over here 1, and chlorine 35.5.
So this should be 1 plus 35.5 is equal to 36.5. Lastly, hydrogen 1 times 2, and we need to add the sulfur as well. Sulfur is over here, you can see 32. So this would be plus 32. This becomes 34. Okay, now fastest rate for diffusion would be the lightest gas. So the lightest over here is 30. You can see 30 is the smallest number. All the other numbers are actually bigger than this. So B has to be the correct answer. I hope this made sense. Next, which gas is the fastest? So hydrogen, you can see, has one. So this, we have two hydrogens, so two over here. Carbon has 12, so this would be 12, plus hydrogen has one, so four of these, 16. Carbon once again 12, plus oxygen, you can see, has 16, so this would be 16 times 2. This should be 30, 32, plus 12, 44. Then we have sulfur. Sulfur is 32. You can see over here 32, the bigger number of course, plus oxygen is 16 times 2. This should be 32 plus 32, 64. Okay, now fastest rate of diffusion would be for the lightest one. The lightest one definitely is hydrogen, so A has to be the correct answer. Which two gases will diffuse at the same rate and at the same temperature? Temperature is constant, so this would depend on its MR basically. So let's find for carbon monoxide. Mono means single oxygen. So carbon is 12. You can have a look over here. Carbon is 12 and oxygen is 16. So mono means single oxygen in this case. Mono means one. So this should be 28. Now over here we should have 12 plus di means 2. 2 multiplied by 16 for oxygen. So this should be 44. Once again, carbon monoxide 28. And by the way, nitrogen is over here, and this should be diatomic. I told you guys during the lecture that apart from group 8, all these gases in group 8 would actually be, like for example, helium, neon, argon, and as we go down this column, all these would be monatomic, like single atom form, and rest of the gases would be diatomic. So nitrogen gas actually has to be in N2 form, oxygen gas has to be in O2 form, and so on. So nitrogen over here has to be in N2 form, and we have 14 over here. So nitrogen gas would be 14 times 2. So this actually becomes 28. So nitrogen has to be in N2 form like this, like two atoms of nitrogen chemically combined together. So 28 and 28, B has to be the correct answer. For chlorine, it would be 35.5 times 2 basically, because this would be in Cl2 form as well. 35.5 times 2 would be 71, and fluorine would also be in diatomic form. 19 times 2 would be 38, so not the same. And once again, nitrogen over here should be 28, and oxygen would also be in O2 form, basically two atoms of oxygen. 16 times 2 would be 32. So only B has the same masses. B is the answer. Next, 4 experiments, each containing a different acidic gas, are set up as shown. The dividing glass plates are removed at the same time. In which set of apparatus does the litmus turn red first? So we look at these gases. It would turn, there would be a change in color when the movement is fastest. And the movement is faster. So we already calculated for carbon dioxide in one of the previous questions. So basically 12 for carbon plus 2 times 16 for oxygen, it was 44. This is HCl 1 plus 35.5. Periodic table would be given, of course, 36.5. And this is NO2, so 14 plus 16 times 2. This should be 46, I think. Um, and we have S and O2. So S has 32 plus 2 times 16 should be 64. So we are looking for the smallest molecular mass so that they are moving the fastest. So in which they are moving the fastest, that would show the red color first in this case. So in B, they are the fastest. You can see smallest MR. So this has to be the answer. Okay, now which gas will reach the center of the room first? So once again, we are looking for the fastest gas. NH3 14 plus 3 is equal to 17. Argon would be in a monatomic form because this is in group number 8. You can see 40 for argon, and for carbon monoxide 12 plus 16 should be 28. So for chlorine 35.5 times 2 71. So in this case they are asking will reach the center of the room first, so whichever is the fastest, that means the lowest molecular mass is the correct answer. 17 is lower than all the rest. Two containers, one of methane and one of butane, are placed at the same distance um, from a naked flame. Both gases are released at the same time. The methane gas reaches the flame. Methane is basically CH4. Gas reaches the flame and catches the fire before butane gas reaches the flame. Which statement explains this? Basically, you can see reaches first, so this would be moving faster, of course. If it is moving faster, it has smaller molecular mass. Smaller mass. So methane molecules have smaller mass than butane molecules. That is why it diffuses faster. D has to be the correct answer. Why does ammonia gas diffuse faster than HCl? HCl's mass is 36.5, which we have calculated numerous times now. Ammonia 17. So you can see lower, smaller molecular mass. So the relative molecular mass of ammonia is smaller. That is why it diffuses faster in this case at the same temperature. D has to be the answer. Which process provides the best evidence for the particle theory? As I already discussed, the diffusion takes place because of random movement of particles. Kinetic particle theory states the particles are in constant random motion. So diffusion would be the process that best explains this. B is the answer. The diagram shows an apparatus used to compare rates of diffusion at which labeled position did a white deposit of ammonium chloride form. So this is hydrogen chloride gas. So basically HCl. So you can see hydrogen has one over here, and Cl 35.5. So this would be 1 plus 35.5 is equal to 36.5. And over here we have ammonia NH3. You can see nitrogen is 14. So 14 plus 1 times 3 would be 17. Okay, now that we have figured the masses out, so you can see this is smaller. That means this would be faster. This should cover greater distance. HCl is slower, so the reaction should take place closer to uh, HCl, the gas which has a more mass. So you can see D is closer to this end, so D has to be the answer. This ammonia travels further. C is more or less in the middle, and A and B are actually closer to ammonia. That would basically show that HCl is traveling faster. That is not the case. Ammonia should travel faster. D has to be the answer. Which statement explains why the gases C3H8 and carbon dioxide diffuse at the same rate at room temperature and pressure? So basically, this would be 12 times 3 plus 1 times 8. So you can see 12 comes from here and 1 comes from here for hydrogen. So this would be 36 plus 8. This should be 44, and this should be 12 plus 16 times 2. This should also be 44. Basically, they have the same mass. So they have the same molecular mass. That is why they diffuse at the same rate. Okay, now a drop of bromine is placed in the bottom of a gas jar. Brown fumes of bromine vapor slowly spread through the covered gas jar. Why does this happen? So this, of course, would be due to kinetic particle theory. So any statement or diffusion. So B, you can see bromine molecules and the molecules in air are always moving around in constant random motion. That is what causes diffusion, movement of high concentration to low concentration. Which correctly describes the molecules in very dilute. Very dilute basically means more water, less sugar. Concentrate would mean the opposite, like less water, more sugar. So which correctly describes the molecules in very dilute sugar solution at room temperature. So we have less sugar molecules, so we have few and far sugar molecules in between, so they should be spread widely apart.
and of course they would be moving at random due to kinetic particle theory. So they should not be close together. They would have been close together if it was concentrated. So A is out, and let's have a look at the next options. It should be moving around. You can see over here not moving, because it is in a liquid. It will eventually dissolve as well. So it should be moving around. Um, as far as water molecules are concerned, we have more water molecules, so we should have larger quantities of water molecules, so they should be close together, and they should also be moving at random, because they are in a liquid state and they can move around randomly, sliding over one another, right? So the correct answer has to be B. You can see not moving for this, so C is out as well. Next, the diagram shows a diffusion experiment. Which gas, when present in the beaker over the porous spot, will uh, cause the water level at Y to rise? So basically, we want it to go up over here at Y. If you want it to go up, this part should be pushed downwards. So when this goes downwards, this water has to go somewhere. It won't magically disappear. So it will be pushed upwards on this side. We want this to rise. So if you want this to rise, basically we want gaseous particles to enter inside this part. We want gaseous particles to enter this part. If we have more gaseous particles coming inside, so these particles would actually push this water level down here and upwards on the Y side. So which gas, when present in the beaker over the porous spot, so over here basically, will cause the water level at Y to rise? So we want any gas that is lighter. So if it is lighter, it will be basically pushed inwards, it will go inside, and because it would be diffusing faster. So if it would be pushed inside, there would be more of these particles inside this jar. This porous spot, basically porous means there are holes in it, so gases can be allowed, gaseous particles can come in and come out. So we have oxygen molecules inside. Over here you can see oxygen has been marked, so this would be O2. So this would become 16 times 2, the mass 32. So we need a gas which is lighter than this. It should be less than 32, because inside we have 32, the mass. So let's calculate for carbon dioxide. 12 plus 16 times 2, this is actually 44. This would actually do the opposite. More of oxygen molecules would go out, and this Y level should actually move down in this case. So let's have a look at B. 35.5 times 2, this would be 71. He's out. You can see 35.5 for chlorine, that is why I times it, I multiplied it by 2. 12 plus 4, this would be 16. Now this is less than oxygen, so more of these, if we have 16 mass here and 32 inside, more of these would go in because they are moving faster. So when more of these go in, this part would be pushed downwards and Y would be pushed upwards. So C has to be the correct answer. For D, this would be 14 plus 16 multiplied by 2. This should actually give us 46. So 46 is bigger than 32. We needed a mass of less than 32. So the correct answer has to be C in this case. So next question. Which balloon would go down the quickest? So an inflated balloon goes down. This is because the particles are moving outside. So the gas from inside basically moves outside. So the one with the smallest mass would go down the quickest, because those gas particles would move out the fastest. The fastest diffusion basically is what we need to find out. So for this first one, 12 plus di means 2 oxygen, 16 times 2, 44. This would be 12 plus 4, 16. This would be 28, basically 14 times 2, and this would be 16 times 2 is equal to 32. So the smallest would be B, the smallest mass, so fastest diffusion, so it goes down the quickest. Why does neon gas diffuse faster? Because neon, you can see neon has a mass of 20. Meanwhile, carbon dioxide, which we have calculated numerous times, would have 44. So this has a lower molecular mass. So neon atoms have lower mass. That is why they diffuse faster. A is the answer. Next, which
So we have these two jars, nitrogen dioxide over here, air down here. The glass plate is then removed. Which of the following correctly describes the colors inside the gas jars after a long period of time? So we are giving it enough time for all of it to evenly spread out. When they evenly spread out, just like our example when we were doing the concepts for potassium manganate, when they are in a liquid state, after 4 hours, the color was evenly spread out. So if you give it enough time, the color would be uniform throughout it. This specified long period of time. So we are looking for evenly spread out colors. So brown and brown, these are evenly spread out. So A is the correct answer. None of the other options shows evenly spread out colors. Which gas diffuses at the same rate as nitrogen gas? Nitrogen would be 14 times 2 is equal to 28. Basically, this would be in N2 form, two atoms of nitrogen diatomic. Carbon dioxide would be 44, carbon monoxide should be 28, neon you can see over here is 20, and sulfur dioxide should actually be 64. So same as 28, so that would be the option B over here. Which property of gas affects the rate at which it spreads throughout a lab? Its mass, of course, molecular mass as well as temperature, but for a gas it would be molecular mass because we assume that temperatures are constant. Which gas has the slowest rate of diffusion? So heaviest gas is what we are looking for. The lesser the mass, the faster the rate of diffusion. So for ammonia it would be 17, this would be 16, this would be 32, this would be 28. So the masses, so this is the heaviest, so this would be, the C would be the answer. Oxygen would be the heaviest in this case. So slowest rate of diffusion. A beaker of nitrogen is inverted over a porous pot containing carbon monoxide as shown. The water level does not change. uh, what is the reason for this? If there is no change in the water level, that means whatever is the mass over here, it should be the mass inside as well. So there would be same mass. That is why there is even like the same number of gaseous particles are coming in as going out. The rate of diffusion is constant. So that is why the water level neither rises nor falls over here and on this end as well. So the two gases must have the same mass. That is why no rise or fall. So D has to be the correct answer in this case. The cover plate is removed from a gas from the gas jar shown in the diagram after several days. Several days. So we give it enough time. The color of the gas is the same in both jars. Which statement explains this change? This must be due to diffusion, and diffusion occurs due to kinetic particle theory, that is random movement of particles in all directions. So B is what explains the kinetic particle theory, random motion of particles. In a sample of air at 25 degrees Celsius, we have these gases all move at different average speeds. Which of the following lists the molecules in order of decreasing average speed? So carbon dioxide, CO2, mass of 44, then we have oxygen, mass of 32, basically 16 times 2, nitrogen N2, 14 times 2 would be 28. So this should be the fastest and this should be the slowest. So carbon dioxide has to be the slowest and nitrogen has to be the fastest. You can see B is the correct answer, oxygen in between. B is the answer. Next, we have methylamine. This has been given. Actually, they have given us the mass as well. The mass of this has been given. You can see 31 and HCl 36.5. So although they are very close to each other, but still this is heavier. So this HCl would be heavier. So this is slow. This is comparatively fast. So whichever is heavier, the reaction would take place towards that side, closer to that side. So you can see we have HCl over here. This is slow. This is slow, but it should not be too close to this. The reason being, you can see the compare the masses. If the difference in masses is really big, so for example, one of the masses, let's say 16, and the other mass is, let's say, 32. So there is a big difference in this case. So it would be more closer to the bigger mass in that case. But when the masses are more or less similar, although HCl has a heavier mass, but 31 is not that far away from this. So it would be closer to HCl, but not too close. So A is definitely out. this is faster, so it won't be closer to this. And B seems like some exactly in the middle, so B is out as well. You see, C looks like a logical option because I think this is the middle. You can check it from with the help of a ruler as well. C is actually closer to HCl, but not too close. D would mean like the difference is too big. Maybe this could have been 20ish, and this could have been maybe 30ish in that case. Like the difference is comparatively bigger. In that case, D could have been the answer. But C has to be the correct answer over here. It should not be too close to HCl because the difference isn't that big. Next question, the apparatus shown in the diagram was set up over a period of time. How will the water level at X change? We have hydrogen over here, H2, and the average mass of air we can take around 20ish. 20ish. So in this case, the lighter gas it diffuses faster. The lighter gas it diffuses faster. So this hydrogen will go inside it. They are saying at X, right? So this moves faster. When it moves faster, it will diffuse faster, and more of it would go inside. When more of it goes inside, there would be more gaseous particles pushing the water down here. So this should actually fall first. Initially this should fall, but later on, let's say after 10 minutes, there would be more hydrogen particles over here as compared to outside, because all these particles outside would have come inside, right? And there would be less H2 particles over here. Diffusion is movement of particles from a region of high concentration to low concentration. Now these hydrogen particles actually need to go outside down the concentration gradient. When they go outside, this should actually start rising. Then they should start rising, and eventually it will return to this position X because there would be like more of these would go out. So it would eventually return to position X. So we are looking for falling then rising. So at A you can see it will fall then rise and then return to X, right? So A is the answer. Now in B they are saying fall, that's fine, but remain at a lower level. No, when there are more H2 particles inside, they actually need to go outside as well down the concentration gradient. So this can't be the answer. It will rise, not really. It actually falls initially. So the correct answer has to be A. Now we are moving to theory questions. Uh, Now we have aqueous ammonia releases ammonia gas. Ammonia gas turns damp litmus paper blue, and you can see we have litmus paper on this side, ammonia over here. At first, the litmus paper does not turn blue. After a short time, when we give diffusion enough time to take place, this is basically wool soaked in aqueous ammonia. Aqueous means liquid ammonia. So liquid won't reach the damp red litmus paper. It actually needs to dissolve, not dissolve in this case, convert into a gaseous state first, because this is a liquid state. So for it to go to the other side, it has to convert it to a gaseous state. So it needs to evaporate first. First evaporation occurs, then diffusion. We need to explain diffusion as well because this is worth 3 marks. At movement of particles from a region of high concentration to low concentration. Then they specified in terms of kinetic particle theory. So we need to state that it would be due to constant random motion. Let's start. Evaporation occurs. Evaporation of aqueous ammonia takes place, and the gas particles then diffuse and reaches the damp red litmus paper. This is movement from high concentration to low concentration because of constant random motion of particles. Let's try to fit all this inside these lines, and this would fetch you all 3 marks. Now, once again, we have been given crystal of cobalt chloride, and at the start, after 2 hours, like not evenly spread out. When you give it enough time, 2 days, it evenly spreads out. So in this case, this is solid converting into a liquid state. Before we had liquid converting into a gaseous state. That is why we said evaporation. In this case, we need to state dissolving. So you can say crystal dissolves and particles spread out due to diffusion, which is movement of particles from high concentration to low concentration due to constant random motion of particles. This is why diffusion takes place, constant random motion of particles. Okay, next up, the question is about halogens. We have been given this, and they are saying um, bromine is a red brown liquid. A drop of liquid bromine is placed um, in the gas jar. After 20 minutes, the red brown color has spread throughout the gas jar. Okay, now first of all, we need to explain diffusion. So same concept over here, and you can see drop of bromine. So it has to evaporate first. So you need to explain evaporation, just like the first example. You can see this one. You just need to copy this answer over there, basically. So it has to evaporate first, because you can see drop of bromine. So evaporation takes place, and then you need to explain diffusion. In the next part, you need to explain diffusion, that it is movement. This is diffusion, and that would be movement from a region of high concentration to low concentration. And why does it take place? Due to constant random motion of particles, right? So this will get you all 3 marks. You can see they specified kinetic particle theory. Basically, just copy this answer that I wrote over here. uh, Over here. Okay, now the question is about the first 30 elements in the periodic table. Name the element which is the gas with the slowest diffusion. So this would be the heaviest gas. Now most of the students, the first 30 elements. So let's start counting. This is one. You can see the proton numbers are written down here, up here rather. These are the proton numbers, and they increase by one for every next element. So the 30th element is this element, and we know that only gases can diffuse. So gases are actually in this part of the periodic table. Over here we have metals and solids mostly. There are a few exceptions, but generally speaking, so these would be solids. So we are looking for gases. So it should be somewhere in this particular line, because as we go to the left, these are solids. So eventually we reach this point. Now most of the students, what they do is they just answer argon by looking at this 40. But you see chlorine, argon would be in a monatomic form, just Ar. So the total mass is actually 40. But have a look at chlorine. This would be diatomic. This would be in a Cl2 form. So this would be 35.5 times 2. This mass would actually be 71. And compare it to argon, although that is later on in the periodic table, but because chlorine is diatomic, so this would be heavier. So over here we need to write chlorine. Slowest would be chlorine because it being the heaviest in the first 30 elements, and it is a gas. Solids, in solids diffusion cannot take place. Okay, identify the element. We have been given a list over here which has the highest rate of diffusion. So lowest mass is what we are looking for. So cancel out all these solids. These are solids. Nitrogen is N2. This should be 28. Oxygen is O2. This should be 32. Fluorine should be, you can see 19 over here. 19 times 2, this should be 38. And neon, this would be monatomic, only Ne. This is monatomic. Group 8 are monatomic, right? So this would be 20. So the fastest rate of diffusion should actually be neon because of its lowest mass. All others would be all other gases. In this case, nitrogen, oxygen, fluorine. This would be in diatomic form. Next question. Uh, choose from the list of these formulas of gases which diffuses most quickly. So carbon monoxide, this would be 12 plus 16, 28. This 40, this would be 44. This would be 16. Uh, this should be 46, I think, and this should be 64. So we are looking for most quickly, so that would be the lightest gas. So the lightest gas would actually be methane CH4. We'll circle it because they specify draw a circle around it like this. Explain your answer. So we'll say lowest. This has the lowest molecular mass. So lowest. The reasoning behind it is lowest molecular mass, lowest relative molecular mass, right? So this should be the answer.